So today I am, well, we'll see how far we get, going to go look at some bigger data, big enough that it was sort of a pain in the butt to do something with, which was the point of the class. And then I got stymied by AWS's like baroque and opaque mechanisms for launching and running clusters, and so I just barely got a cluster going before class. So I'll have some slides from that, but I'm not going to demo that or ask you to demo it right away. And we'll see if we can't get something easier going for the next go round. But so today I'm going to look at a 12 gigabyte file, 12 gigs on disk, 123 million rows. So now this is getting big enough to become sort of obnoxiously big. This is all the air flights for the last 20 years. And there are like 31 columns in there, including 29 different carriers. There's 350 different origin destination airports, flight numbers, tail numbers, a bunch of stuff on was the flight delayed and what was the reason for it being delayed. And the goal here is to build a model to predict that your flight was going to be delayed at the time you buy a ticket, not after the fact, right? This is no fair predicting that your flight was delayed because you looked at the canceled flag in the data set. Or in the security delay flag, or in 15 other delays. Do this on only data that you have available before you start the flight. So we want to go look at the data. So in this case, I said, okay, I'll start with easy. I'll grab my home machine, which is a 4-core, 8 hyper-threaded, 32 gig machine. I launched a 24 gigabyte JVM instance to load a 12 gigabyte data set. Well, it took about 20 minutes to load that data set down over a pretty good internet connection. Once it was downloaded, it only took a little over a minute to get it into an H2O instance, and then I get to peek at the data. Right away, I just say, hey, let's go predict on is arrival delayed. There's a lot of columns in there. We'll look at arrival delayed, and we'll run. Okay, that takes 7 minutes, 40 seconds, so quite a while. And it's long enough to start getting obnoxious to want to do any sort of serious modeling work, because I'm going to have to be waiting, 8 minutes every time I do anything. And so, this sort of limits how fast I can go. And then, of course, the first model comes back completely ridiculous. Perfect AUC. You can't see this one here, but the blue AUC curve goes all the way up to the corner and then cuts across. And that's because it's just predicting on the number of minutes you were delayed. So if your arrival is delayed, true or false, well, if you have minutes of delay greater than 0, then of course you're delayed, right? Okay, so throw that one out, throw out departure delayed, throw out is departure delayed as a Boolean flag. It was also included in the data set. Run again, another 8 minutes go down, get a more realistic AUC. It's not perfect fit, but then I'm predicting on canceled. Okay, your flight was diverted. The carrier had a delay, but they don't tell you why. Late aircraft delay, the prior flight was late coming in. So there's a bunch of stuff going on here. It's like, no. There's a lot of things that you could use to predict on. And this is sort of a common, easy fallacy here. The data sets you get will typically have a lot of information about negative issues that they're trying to solve for and figure out. And the information they'll include will be stuff that's not available ahead of time typically. Right? So you have to go sort through the data sets and say, no, this doesn't make sense to throw out. So I ended up throwing out, I'll take a quick aside here into logistic regression. So let me back up for a second here. I'm running GLM, generalized linear modeling. I'm actually predicting on a true or false value. So I'm looking for a logistic regression, logical, right? So logit notion, true or false. And I'm using generalized linear modeling as an easy, fast technique to do something. So generalized linear modeling fits a best fit hyperplane through the data. And here I have a two-dimensional with a best fit hyperplane is one-dimensional, it's a line. There's your best fit line. Okay, fine. But it also then pushes it through a general function afterwards, the response variable, the thing you're trying to predict on. And if that extra function is the identity function, you get a Gaussian regression. It's a continuous variable. It's suitable for predicting things that are continuous, like gas mileage on vehicles or average time or velocity or something like that. But we want to do a logical thing, a true-false. So we push it through a logic function. The logic function has an output, makes an S curve, like a bottom curve there. And as it goes down towards 0, you're more likely to be false, and if it goes to 1, you're more likely to be true, and you get a probability out of it, right? So it's like 90%, 80%, something like that. Like this is the odds kind of thing. But to get that to happen in the generalized linear modeling framework, you have to ask for it. So a easy fail is to simply hit the go button on GLM when you want a logistic regression. You go down to the family and say, don't predict on a continuous variable from 0 to 1 as a straight line. Do it as a logic function and give me an odds, a probability that it's true or false. Otherwise you get the wrong prediction, and the continuous thing goes above 1 and below 0, which makes no sense if you're looking for true or false, right? So you don't want a line, you want the S-curve thing. Okay, so back to my big data. I ended up throwing out 17 columns out of the 31 that all had some flavor of prediction. And another 8 minutes go by, and I get a really lousy model out. So I'm predicting on things like, well, the time in the air. Not the time, the planned time in the air and the distance. So there's something that says, if you have more time in the air, you're more likely to be on time, because presumably the pilot can goose the throttle a little bit and make up for lost time. That's my guess. Turns out that if you're flying on PI, which is a now defunct airlines, Polar Airlines, you're like never on time. And that's because I guess if you're going to the North Pole, you leave when you're ready to leave, and it has no relation to anything else.
Is this only domestic or international?
No, this is all flights in the world.
Okay.
This is international.
Okay.
So, there's other things in here like, Hawaiian Airlines from Honolulu is very much on time. I guess, it's easy if it's always sunny. But if you're coming out of Atlanta or Dallas-Fort Worth or JFK, life kind of sucks. So it's a reasonable set of predictors. It kind of matches my intuition. But the model itself is pretty lousy and slow. So I know that generalized linear modeling is highly parallelizable, and maybe my home machine's not so beefy. Maybe I can make it better. So now the rest of this talk is going to be about a horrible dive through ops. Not data science, not computer science, ops. And IT. And this is common for dealing with data in the data science domain. Some interesting large fraction of your time will be spent screwing around with obtaining and dealing with large chunks of data and machines that can deal with them. And dealing with machines means finding a machine, logging into it, logging out of it. SSH, security protocols, IPs, internet protocol ports, all that kind of stuff. So I put together this quick plan of attack. I'm going to run a cluster of 4 machines just to see if I can do it. And the first go is I'm just going to run it on my laptop, right? And then I know that the way H2O works here, by default he uses multicast as an easy, quick go, but that's not going to work in EC2, and it's not going to work in any data center. Multicast is great for home machines and completely wide open networks. Every data center on the planet has some sort of security lockdown. The first thing they kill is multicast. So it's nice for development work. It doesn't work in the real world, so you have to know how to do the other option, which is flat file. So what is flat file? Flat file is a list of IP addresses and ports that are the members of a cluster you're trying to build. So you're trying to get a set of machines to cooperate. They have to talk to each other. They have to know the names of all the other machines. On the internet, your name is your IP and a port.
I have a quick question. Here the IP is the static and dynamic aspect matters, or?
It's whatever IP you get. So typically...
So is it real time? Like if I have dynamic IPs, then this like...
Dynamic IPs are assigned at the time that you ask for an IP address, and then they don't change. Okay. Typically you get a lease on an IP address at an IP for a day or a couple of days. Okay. So it's not the case that the IP address flips on you sort of continuously. It will, however, change every time you bring your machine up. So if you walk your laptop into a Pete's and you get an IP address from Pete's, that's good for the day, but it will be different every time you walk into Pete's. Right? So that same Pete's will hand you a different IP every time. And if you reboot your machine and he forgets the old IP, when he goes to ask for one, Pete's will hand him a new one. So your IP address will change sort of every time, but once it's set on that particular instance of your machine, it's there. Same with EC2. When you go say, give me some EC2 instances, they'll give you an IP address. And that will be different every time. So there's places in here where you have to plug those IP addresses out throughout. right? Okay, and that's the thing you have to be aware of. What are my IP addresses right now? And we'll see instances of that as we go. Yeah, go ahead.
Is the configuration of like the programs you need to analyze data in the flat file, or is that somewhere else?
No. So the flat file is simply how the cluster is going to communicate. It's not necessary if you have one node, because you didn't have anyone else to talk to. As soon as you only have more than one, they have to know the names of the other guys.
Okay.
So multicast is effectively shouting, "Hey, I'm here. Are you here?" on the, in the network. And that kind of shouting like drowns everybody if everyone's doing it. And so the first thing data centers do is cut that off. So if you can't multicast how you do it, you have to have a name handed to you. And that's what the flat file is.
I have one more quick question. So let's say if in a simple setting like I have Stanford network, then I don't need to change the flat file again and again because one of the computers might not go to Pete. But if one computer does go to Pete, I need to be aware that
It depends on how Stanford sets up their networks.
okay.
So you can get static IPs, and those will not change over time.
Right.
Typically, that's a 4-pay extra feature that's not done.
Okay.
So on your home machine, you can go to Comcast and pay an upcharge for your home internet and get a static IP. And they will bill you some interesting monthly fee for that static IP, and forevermore it's the same. Otherwise, your IP is dynamic and will be different sort of every time you bring your machine up, on the internet.
If I create a VPN, would that solve the problem?
No.
No.
No, and in this case, you don't want to because you want the machines to talk to each other directly without going through a security protocol. So they're going to be doing math at high speed over a TCP connection between each other.
Yeah.
So at every layer you add there is going to slow down. And the goal here, one of the goals is to get more memory for bigger data, but I have enough memory for this one. The other goal here is to get more CPUs. I don't want more crunch time, so I don't want to burden them with any extra stuff. Okay, we've all read this 14 times over. I'm going to skip it here. Yeah, okay. So the first thing I'm going to do, I'm going to make a cluster for my laptop using multicast because it's too easy. And this is just, by this point, I'm hoping everyone has been able to fire off H2O. And here I just did java-jar, H2O.jar, put in the background, second, third, fourth. A bunch of output scrolls by, and after a while, I'll see cloud of size 4.4. Takes about 2-3 seconds. I didn't do anything. I just said Java, 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 Java from a command line. Went to Flow and looked, and he says, okay, you got 4 instances. They each have 4 cores. So of course, it's the same 4 cores, so you don't actually get any more horsepower. But he makes a cluster. So there's something in the technology that works. So this is just to confirm for yourself that you can do this. So you know that it will work in the simplest, most obvious case. And then we're going to start ramping up the difficulty as we go. Because along the way, you'll have all kinds of fails that will differ according to whether you're a Mac or a PC, whether you're Ubuntu versus Red Hat versus whatever, whether you've got some sort of security thing going on, like you're in an AWS instance, there's all kinds of security protocols you have to deal with. So it's good to know something works. If this doesn't work, you have to go fix that first before you go to the next step. Okay. The next thing that happens is that you'll end up with extra JVMs lying around by mistake, both in EC2 and on your laptop. Kill them, or they'll end up fighting with other clusters you're trying to start up, and you'll just get confused as to old versus new versus whatever. A lot of ways to kill things. Hopefully everyone's got enough OS experience they can hit Control-C or bkill Java. There's a couple different varieties here, right? You can do a shutdown if you get to the web interface. On an EC2, of course, you're getting billed for your instances. So I spent about 2 hours last night, 2 hours this morning, maybe 4 hours yesterday, and 2 hours this morning on EC2. The total bill is like $3.50. Nonetheless, if you forget, leave an instance running for a week, you're not going to be happy. So shut them down and just double check that they're gone. Okay, so that one was too easy. So I want to go do the next harder step. I'm going to use a flat file on my laptop as a practice. So the flat file is the list of IP addresses and ports, 1 line per node in my cluster. So I want to make a 4-node cluster just to get started here. So it's whatever IP address I get out of my laptop. This will not be your IP addresses. People frantically rushing forward to scribble. Okay, these are not your numbers. These are not the numbers you're looking for, right? You have to get your own IP addresses. Now the port numbers were probably correct here, because by default H2O starts at 54321, but then if that port's in use, he just bumps by 2 and goes to the next port. So by default you'll get 1357 on the last digits there for the port numbers. On EC2, everyone will have a different IP address. So port 54321 will be open for them all. So all your nodes will all have port 54321 by default, but they'll have completely different IPs.
Why does it use odd numbers of it?
Because it actually uses 2 ports. And so he needs to, so 54322 is also in use. So there is a separate port being used for the web console and for machine-to-machine communication. Separate TCP port. And UDP is also used during the node discovery mechanism. Once you have this file, it needs to be handed out on the launch line. So my launch line says Java jar, H2O jar like before. The IP number here I don't need to put because it's the same on the same as my laptop. And EC2 will be whatever it is on EC2. So I don't actually need an IP here. The port I don't need on EC2 because it's always 54321 by default. But if I'm doing it on my laptop, I need to say this, or I need to know that they're going to bump by 2. And finally, say dash flat file and put the flat file in, and then I can launch 4 in a row with the flat file.
So you do that command 4 times. It won't automatically launch 4.
That's right. This launches 1 instance. So I'm doing this on my laptop, so it's still same old, no more horsepower, right? And so this launches 4 in a row. The first one out the door will get 54321 by default.
Right.
The second one out the door, we'll see that 1 is busy and bump to 3, and then bump to 5, bump to 7.
Okay.
That matches my flat file numbers,
Right.
and so it all works.
Right.
But if I had different port numbers, I would need to, I wanted to specify, I could say here and say here different port numbers, and that would fix any issue about having him hunting and guessing for what ports are available.
But the flat file doesn't automatically launch 4 instances.
No, the flat file is only telling the instance that you launched where to find his brothers.
Okay.
Right? This is the launch, Java.
Right.
Right? So that's one launch. This just says, where do I find my brothers?
Right. Okay.
And when I'm on EC2, they're going to be scattered around, and I'm going to have to tell them where to go find each other. Okay, and again, these slides will be online. There's a lot of detail in these slides that you should be able to read. We'll put them back on the ICME website. You can go read them there. So then I'm going to go play around with EC2. And half the issues I'm going to have with EC2 are one-time setup issues that you all have to go step through. And I'll throw out the one caveat here. You don't have to use EC2, but I am going to hand out data sets big enough, it's going to be a pain in the butt unless you have a cluster available. There are other places to get clusters than EC2, but EC2 is cheap and available. So internal to Stanford, large numbers of groups run clusters. I just couldn't get one available for people in this class as a reliable resource. If you happen to have one, then you can take advantage of it. Including if you're, you and your roommates at home between you have 3 or 4 machines with a couple hundred gigs across the set of them, you can do it at home. Right? There's no requirement for EC2 or an Amazon here. It's just this is like $5 and a couple hours worth of work, and a lot of annoying detail work to figure out. Okay, so make your own free account. Amazon says that they'll give you $35 in funny money if you sign up for the AWS Educate using a Stanford email address. I don't have a Stanford email address, so I didn't get this, so I didn't test this one.
When you sign up, it asks for like an enterprise account or a personal account. Now, I saw that there's an enterprise agreement with Stanford. Have you looked into that?
So that agreement was not signed as of a week ago when I was talking to the AWS folks. So I don't know, or the educate part was not turned on. There was something that said that they were not ready to go with students using that account. They were working on it, that was last week. Maybe it's all better now, I don't know. I claim you use the standard AWS Educate sign up and step through it, and it should let you get to the Funny Money account straight up. They'll want a credit card for when your Funny Money runs out. You should be able to do this entire class without running the Funny Money out. But I do not take responsibility if you leave on 8 big servers and go on vacation for a month. Amazon will be happily bill your credit card, and your problem. Within the AWS, there's like an East and a West Coast and some Europe and all that. I take Northern California as a region, and I shove the data there. And so when you go pull the big data over, it wants to stay within the region, or else your carrying the data like over the internet, across the continent, right? So it's going to go faster this way. There is a tutorial for launching an instance. It was pretty good. It took about 10 minutes. Okay, step through the tutorial. Pay the price, burn your 10 minutes. Somewhere in there will ask you for what size instance. He's recommending the free one. Take it. It's great to get your setup figured out. You'll have to make a key pair. I talked about this last time. You'll have to make a key pair. You'll want to make a placement group, which is just a name. And machines that are launched with the same placement group are encouraged to land near each other in the networking sense, like on the same rack. So you don't have like giant networking hops all over data centers. And you'll want to make a security group, which I'll talk more about later on. And once that happens and you launch the sucker, it takes about a minute, and then the web page in EC2 pops up and says, you have a public IP address for this instance, and that's your access from outside AWS into it. And then, here's my, you can't read it, I'll show you in a second here, but somewhere here I said, go SSH here. I gave it my key, so it's a key pair. Here's my private key. Here's my IP address. This will be different every time you launch. And then I could SSH into the box. And the key here is I have to have this key file matches the one I saved locally at the time I'm doing a key pair. And the IP address is the one I got from AWS. And I'm able to launch in and run Java version from a SSH shell. Having done that, I need to go get an H2HR file to launch. And so wget of this address. So this is a Amazon bucket, S3 bucket. In the S3 bucket is H2HR file, a small test file of airline data called Airlines 2K. It's like year 2000, 50,000 rows or 45,000 rows. And this 12 gigabyte airlines file, a really big one.
I have one quick question. So let's just say you have 4 nodes. One has this OpenJDK and the other one has that there's this Oracle.
They
blah,
won't.
blah. They
will not.
They will not work then?
No, they will not have that. They will only come up with OpenJDK unless you go ask for Oracle.
So, but my question is, as I say, I was working with 2 different computers and one had an OpenJDK and one had Oracle.
Okay.
Would there be issues?
I don't know. I've never tried that configuration.
Okay.
Run once, whatever. Write once, run anywhere says it should all work. There's nothing going on.
Because while you install AWS, it makes you install the Java part, right?
No, the Java part came pre-installed in all these instances. I didn't do anything to install Java. And it came installed with this version of Java.
So there's a difference between the Java you install on your own laptop to run the EC2 tools and the Java that ends up on the EC2 instance.
Right.
So those are different.
So let me stop here and bring up sort of the meta issue. So not everyone in this class has like the background here in IT and ops, and some people probably have more than others. And I ask people to form groups for a reason. It's like puzzle this crap out. So I guess I'm going to ask here: does anyone here mess around enough with AWS, Amazon, or has anyone here messed around with AWS before? 5 or 6 people. Okay. Anyone here messed around? Feel comfortable with SSH security protocols, like how they work mechanically, not the actual math behind it. So again, in many of the same hands. Okay, so if you're not comfortable with how this stuff goes, I encourage you to find other people, and I will ask before class lets out that these same people raise their hands again, and let's see if it makes sense to create groups of 2 or 3 people here where you can lean on somebody else who might be more comfortable with this piece of the puzzle. Right? Okay, so the last thing is that once I got my jar file, I was able to launch. And then I was able to reach into it from Flow or connect it via Python. I'm not showing it up here, but I used the public IP address on Flow, and then it got me into the web GUI. And from the web GUI, I can see instances and see I have a cluster of 1. I can load data. I can carry on from there. The data, in fact, I had loaded, I should have showed in the slide here, was the, maybe I showed the next slide. Yeah, okay, so so having an instance up in AWS, let's go to the next step, which is like, go load data and do something. And I did this in Flow, just because it was quick and easy. But there's a bunch of buttons to click through, and they're mostly click-through buttons because the defaults all work. But the main first one is, I have to import files And the import here I'm using is this path to the same bucket where I have the h2.jar file, and that's the all years, it's 2K, it's actually year 2000, it's not all years. It's the airlines for just year 2000. That's a smaller data set. The other thing I'm doing here is I'm loading it via the HTTP protocol, which is a web browser style protocol. That's fine for a 10, 20 gig file here. This is like a 4 or 5 gig file. You don't want to do this for your 12 gig file, or if you do, it will take a long time. Because that's a one node, single threaded, I'm going to pull the data to one node and then he can distribute it out to a cluster later. So to get to fast parallel ingest, you actually have to teach the guy how to talk to S3 buckets directly, and that's another piece of the setup we'll get to. But this works as a quick start. I just put this path in, and in fact, once I got it far enough along, he started auto-completing on me, and I could get all years 2K, scroll down, hit the import button, and that maps the remote file locally into the H2O cluster's memory. Do a parse setup, which then reads the first few megabytes and says, this is what I think it looks like. For the airlines file, it does a fine job. Use the parse button. It took 3 more seconds to finish the job. And then I could go look at the data. And I get a picture screen that looks like this. There's about 44,000 rows and 31 columns. And I see the data that I was talking about earlier when I built my model. Year, month, day of week. CRS, departure time, that is the planned, the scheduled departure time. That's the scheduled arrival time, but that's the actual arrival time. And then there's an actual lapse time and a CRS lapse time. So obviously if you're predicting delay on arrival, if you allow arrival lapse time into your model, having a giant elapsed time was going to obviously be a leading indicator. But that's not something you have available when you're buying a ticket or planning your trip.
Could wrangling be done at this stage?
Yes. And totally what I'm doing is I'm throwing out columns and building models in a loop.
I have one more quick question. Let's say you have 4 instances and my data set was 500 gigs. Is it what do you generally do? Do you take a big hard drive where you put about a terabyte of hard drive and you put your data, or are you able to chunk the data?
Okay, so that's sort of a different question. That's sort of the mechanics of how the system works with the big data. Each instance, when you load data using the HTTP format I did up here, it's like the browser style input. The data flows into one node, all of it, who then has to hand it out.
Okay.
To do it for a big enough data set, they need to do a parallel ingest, and only the subset of the data. So one node never sees all of it. That's what I was talking about when I said S3, you have to teach them how to find the S3 buckets, which I didn't show in the setup so far. And then, to your point, the other way to pull data in is to put it on the local drive on each node. So each node has some kind of local access to the data, which would be the same data if you have, for instance, NFS, it's a network-mounted file. But if you don't have NFS, then you could just copy it locally on each node.
But isn't it better if, like you said, probably just have a 1 terabyte of per disk, have the 500 gigs on it, and then each node have access to this basically?
So in that scenario, they'll all ask for their slice of 500 gigs, 125 gigs each. They'll all funnel through the network to the one node that's got the disk and pull it off there, and you'll pull data from one disk and then hand it out. And the one disk will go at 100 megabytes a second as a standard good disk throughput for 500 gigs, and that's going to take however long that takes. Do your math. So if you have 4 disks with the data, you get 4 times the bandwidth because you get more spindles in action, right? This is sort of the obvious thing here. As soon as you have a single bottleneck at any point, that is the bottleneck. And this is, the ingest step. So ingest for my 12 gig file was about 70 seconds, and I'm just going to wait it out. But if ingest becomes an hour, maybe half an hour, then I want to start thinking about pulling more disks into play. I don't need to do ingest very often, so I'm willing to let it sit for a little while. But if I'm doing it on a daily basis and it's taking an hour a pop, how much work can I get done if I have to start every action with wait an hour, right?
I still am not able to assimilate this thought that even if I have 100 gigs of RAM, how will I actually be able to view 500 gigs?
So that's a different one, and that's the, you have enough RAM to match the data, and if you don't, it's not going to work either. Right, so somewhere in the world, I've got a disk drive, and I've got, hypothetically a 500 gigabyte data set. Off of here, there's a network. And then, some router, and I got 4 machines here. Okay, if each machine is running at 100 gigs, then I have 400 total RAM. I'm not going to load that 500 gigabyte data set in, because it's not going to fit in RAM. Suppose there are 256 gig machines each, and then I get 200 gigabyte heap. Okay, now this works. It's close. You might get trouble, but in fact, 256 gig, I'll just make them 250 each and leave 6 gigs for the OS and get a terabyte out. Now I have about double RAM over the data on disk, and that's reasonable. Now, how long does it take to pull this data off? Well, it's probably coming out at about 100 megabytes a second on the disk drive. That looks to me like about 5 times 1,000 seconds. That looks like an hour and a half.
Yeah.
So, maybe my life sucks here.
Yeah.
If each of these has a local drive,
Oh, it's already chunked out. Okay.
and I put the 500 gigs on all local drives,
I see.
because disk drives are cheap.
Right.
Right, I went to Fry's, and that terabyte drive was $40 or $100 or something.
Right.
And I didn't, my time was worth more than $100, so I did
But
this.
but they'll have different chunks to look at, basically.
No,
right?
they'll have the whole data set. This guy will look at one chunk of the data.
Right, that's what I meant.
Yes,
Yeah, okay.
yes. So conceptually, they'll break the data up, and this guy will look
Okay.
at this chunk, and this guy will look at this chunk, and so on and so forth.
And this H2O flow does that chunking aspect?
H2O does that. Flow is just the web interface.
Okay.
The difference here is that what is the mechanism for pulling data in? What is the protocol? This one says, go to a disk file. He went into the low-level Java and said, do a file, new file, .seek of the correct offset, .read of however many gigabytes. Whereas the HTTP protocol one said, open a web URL, and there's a stream, and I have to do a file after a stream thing, and then read bytes and read bytes and read bytes or whatever, and I get single stream from this protocol. Now I can use any protocol a browser understands here, so you can get a lot of other protocols. So it's this convenient catch-all, but this is a single-threaded bottleneck, and all the data flows into this node, and then he hands it out to these guys over the network. But it's definitely a lot slower than doing this. Like this will not do 100 megabytes a second, even if the network's fast, because the stack itself, the software stack, is too expensive.
Is that a general rule of thumb, is you want to double the RAM of your...
For H2O, somewhere between 2 and 4x is a good answer. I know about 4x is overkill. I recommend 4x because it just removes problems. But I routinely do it with 2x and it's fine.
So, yeah, is it like bigger the data set, the more you benefit from like a 4x?
No, not really. No, there's some peak memory usage because the data comes in, there's a bunch of compression going on, and there's some extra buffering, and there's buffered copies, and then they get recycled and thrown out. And if you fall over the peak, you get in the GC cycles, and it gets really slow on you. And that's what the 2x versus 4x is. Some of it is the compression ratio that you end up getting out of the data too. Not all data compresses so nicely.
Yeah.
Okay, so after I pull the data in, I'm still, in this example, working on my 44,000 rows small case. I hit build model. There's a drop-down tag for picking GLM. I pick the response variable, which is, is arrival delayed. I change my family to binomial. I threw out a bunch of ignored columns. Otherwise, I end up predicting on, the minutes I'm arrival delayed. Build model takes a few seconds. I can look at it. And this is the same model now running on EC2 that I run on my home machine, except with small data. And I have the same kind of lousy AUC, and of course it's small data, so it runs in 2 seconds instead of 8 minutes. But it was an evidence that I could actually build a model, do something. So then the last thing is I wrestled for hours and hours and hours on getting this to run on big data on 4 instances. And so I'm going to step you through what I failed on and then punt. And we'll have to figure out how the hell that you guys can do this too. So I killed my single instance so I don't get build. Back to my EC2 console. Turns out I have to open up the security, to open up the ports between the instances. Turns out I needed like port 22 for SSH and port 80 for wget. 54321, 54322 for, H2O itself. It was like a pain in the butt. Open all ports, give up on security. It's your homework problem. It's not somebody's bank account. And don't worry about it. It was painful to figure that out. I needed that flat file, which I had to build after I launched my instances. I didn't have the public IPs. Wrote a flat file on my local PC, and then cut and paste it on each of the 4 instances, which meant I did the SSH shell on each of the 4 instances. So this is totally a game I need to have a launch script for that I'm now working on. I'm hoping to be able to hand this out next class period, and then you guys can guinea pig your way through whether or not it works. If you want to fight through AWS, please be my guest. It will help you a lot when something breaks. This is a cut and paste configuration file I had to do as well. Included like your AWS key and secret ID separate from the other PIM file we're using. There's 2 different keys running around here.
I have a quick question.
Yeah.
Secret keys are generated on the local machine or from the AWS. You go on the website and
On AWS. These are all generated on AWS, and then the secret part is handed to you. That you need to write down on your laptop, and then AWS throws their half the secret away.
Okay.
Or so they claim. Who knows? But I believe it is generated at AWS and handed out, hopefully through a secure protocol in the first place, or your keys are getting passed around in plain text. I don't know. Mostly for what we're doing, you don't need any security, so all the security is a waste of time and complexity and causes you trouble, but you have to play the game because AWS doesn't work any other way. I did get it to the point where I could launch my 4 instances, SSH them all, download my jar files, put in the flat file and the SV config file, and get the damn thing up and running. And I got it to go just right before I took off to drive here. So I ran on 4 8-core 32 gig machines. The file load time was about the same versus my SSD drive on my local machine versus AWS versus over S3. But S3 caches, and if I loaded a second or third time, it might have gotten faster. But it still looks mostly IO bound. But GLM ran about 4 times faster. About 4 times more cores, ran about 4 times faster. Theory says if I bought bigger machines, it would run 4 times faster again. And I have seen this happen, so I know GLM will run faster again. So at that point, it was fast enough I could try some other stuff. I eventually tried a gradient boosted machine, took about 15 minutes, not really much better.
So is this one of those, so what you're saying is the performance increase is due to additional cores, not
Yes.
necessarily additional RAM?
That's right. So if the data doesn't fit in RAM, you're dead.
Right.
It's so slow that don't bother. Now that it fits in RAM, the choices are fatter boxes or more cores. And fatter boxes means that you do less network overhead, and more cores gives you more raw CPU, but you need more boxes and therefore more network. GLM is very strongly scaling. If I just add more cores, it just runs faster. And I don't know what the upper bound is, but I have definitely run 1,000 core configurations of GLM and had it be pretty close to, it's not flat, but it's still rocking along. So you can just add more machines and get it to go faster. This amount of screwing around, by the way, all told, counting last night and this morning, cost me about $3.50. So if you find your time's more valuable than that, you might get more machines going and have it go faster.
we could use, let's say, a different algorithm and parallelize it, and then also.
So GVM is a different algorithm.
Right.
So these algorithms are all parallelized and distributed already.
They already.
Oh yeah. Yeah, that's why more cores helps. Because they use the cores, and that's the parallel part, right?
Right.
Distributed as well. GVM does a lot of network traffic. So if you get too many nodes in your network, then that balances off having more cores for compute. this is a big enough data set that more cores will probably help for a little while, but it won't go to 1,000 cores where you'd rather have fewer cores and less network. The other point here, of course, is the model wasn't good enough to be like exciting, right? The GBM took a lot longer than GLM and wasn't excitingly better. And that's because I think we don't have any good predictors. So, up-leveling a conversation, so you get a lousy model and you're trying a different guise, but you're a long ways from something interesting, you probably need better predictors. So looking at the predictors he's using like flight time, the carrier, like some carriers are more reliable than others, the airport, some airports more or less. But, maybe you want to get average daily weather of the day you're going to fly. Like that might tell you something like, what are the odds of getting snowstorm at JFK? Or what time of year does fog roll into SFO? How about holidays and weekends? Right? Maybe weekends, I think weekends are in there, but holidays are not. And, Thanksgiving, right? And Christmas and like those kind of days show up. And what other predictors make sense here? So there's something to be done here. I think having running like hyperparameter search here is like not going to help because you're a long ways off from anything exciting, and that you really want to get to a better predicting model in the first place, which you can probably experiment with small data and go out from there. And then I basically ran out of time, so I'm going to do this announcement and then we'll take Q&A for a while here. So my plan is to by next week put a big data set in S3. And you can either run it in S3 with EC2 or pull it in your own cluster, but the data set wants to be big enough that it's a pain in the butt to do something with. That airlines data set's been around the block a few times, people can get their hands on it pretty easily, know what it looks like, but I'm gonna try and find something that's somewhat different. And on that order of magnitude, somewhere between 10 and 40 gigabytes in size, so big enough it's a pain to do something with. You should be able to get together a Python or R script. So I mentioned in a prior slide that once I had that cluster up and running, I can attach to it with Python. And at that point, the data's in there, or I can load it using Python to load it with the same loading I was using in Flow, however I got it loaded. And then do the column drops, and now I want to do some feature munging. Maybe I want to pull up a holiday list from another website and join that into the current date, time, add holiday data, add weather data, right? Figure something out here. So on these kind of operations, when the data gets big enough that it's a pain to use, you do want to sample while you are model exploring. But you don't know how well you're going to do to get to the big data. So you can load the big data one time, do a split using H2O, and you'll get a nice random split. And now split yourself down to something small, and take that data and go back to your laptop and explore. And start screwing around with what can I do with features to make something happen here. And I would like you to be able to eventually run in your Python R script, a couple different models. Tell me what you did and why you did it. So you dropped some columns. Why? You decided that you wanted to bring in weather data, and you did the same thing I did, and you grabbed some weather file from the internet, and you had to screw around for a while and added weather data. I think any number of some minor munging is going to count good enough to know that you got the right idea of what's going on. And describing why you did what you did. This is not the mechanical, I said SSH into, I launched a cluster. This is using your head to think through what's in the data, what can I do with it, what's not appropriate, what is appropriate, right? Yeah.
Are there any data sets built into H2O, or any way to, let's say, join data sets without doing it manually in Python or downloading it locally? Or?
Not in that sense, no.
Okay.
So the H2O Git repo, if you do the full Git clone of the original source, includes a directory called small data, which has a huge variety of small data sets, many of which are used for testing purposes or demo purposes, including a small version of the airlines and a bunch of other stuff. We don't have built into H2O anything like weather or geographical data, and that's actually no tool does that I know of. And that's because the quality of the data is, and what you want out of it is highly up to the person doing the work involved. So it's not, it's all easy to say, hey, just press the go button on having some weather data in there. And that works for some people, and anyone who's got anything outside of a very narrow domain, wants to know what the hell they're getting, right? And then, the other obvious one that you might imagine being popular everywhere would be geographical data. including every kind of, zip code, average salary, average home price, distance commute, price of gas, blah, 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 that kind of stuff. Again, those data sets are available, but they're not baked in any tool that I know of, and you always end up downloading them, doing a bunch of munging to get the columns to line up properly, and then do a join on it. But the outcome of the join probably gives you a much better model. So,
And we should do this in R, Python, and then.
you should do this in R and Python and on data that's quick and responsive. So, if you're using H2O and R and Python and not the R and Python toolkits that are built in, you're probably fine with data sets that are, some number of megabytes to low gigabyte counts in terms of the interactive field. Once you see that you're getting a good uplift out of your munging work, you need a script that you can replay from scratch. Once you have the script you can replay from scratch, now it's time to go get a big cluster going, pull in the full-size data set, and see what your script does on the big data. So the goal here isn't to get a perfect answer or to beat thy neighbor and get a better prediction. The goal is to see that you did something reasonable and showed that you understand the concepts of test train split, feature munging, and something to do with clustering. And that you could, and then turn the script in is tell somebody else what you did. So it's no good to do your experiments in a vacuum. You have to tell somebody else what you did.
So if the data is really large, like it doesn't fit into RAM on just one machine, and say we wanted to add a column, like a weather column or something, that would be kind of hard to do just on one machine then, right? What would be the best
So if you look at the data ingest rules, I said 2x. And here's the giant set, 500 gigs data on one side and a terabyte RAM on the other. Once the data is in and compressed, it's probably under 500 gigs now.
Okay.
So now you have another 500 gigs to add temporary columns. Any individual column is probably going to come in at 100 megabytes, and you're going to add hundreds of columns before you start running out. So I don't think.
But so we can do joins with H2O and stuff like that? Or?
Yeah. I mean that's the goal.
Okay.
So totally, I was demoing last time doing those weather joins. Those were pulling in data sets that were, after the join they added more columns, but the amount of extra volume data added is not so huge that you actually ran out.
Okay.
If you do it indefinitely, you can run yourself out. If you're exploring and you have a lot of extra columns that are no good and you want to throw them out, the reason to have a script is that you can blow the cluster down, restart it, and then all those temp columns you made along the way aren't in memory anymore, if that turns out to be a problem. Okay, fine, I already said this. That's it. I wrestled too long with AWS to have more talk on it, but it's also very nitpicky, detail-oriented. I'm kind of not happy with AWS right now. So I'm hoping to get a script next time. If that doesn't happen, I'll probably resize the data sets involved that they can be run reasonably on a fat server that you can just get one instance going. Because then that's a lot easier to set up and run on AWS. A 64 gig server on AWS is actually pretty straightforward. It's the same as that tiny guy. It's just bigger. You don't have to have the security holes figured out and have the flat file figured out. So a bunch of stuff gets simpler.
You mentioned before that you had 1,000 core or 1,000 instance.
1,000 cores.
1,000 core.
Yeah. It was 128 instances at 16 a pop, so whatever that comes to in the math.
Where did you get those?
AWS.
Oh, okay. But you got more complex since then, or?
What? I'm sorry?
I guess you said that.
Oh, okay. So I've been working a long time with a bunch of other people who have worked for a long time on scripts to let you launch big clusters in AWS. And I want to get those, get an instance of that. I know exactly where it is, and see what it takes to have it work and see that it's appropriate for people in the classroom to take and run. Because a lot of this stuff that's going on there had pre-cooked setups internally to H2O the company. Including having various kind of Amazon security groups set up and various kinds of performance groups and whatever. And there's some rules with AWS about how big a cluster you can launch that were all cleared already. So if I just grab this script and say, here, run this, and you're not running it from the H2O.ai domain logged in as an H2O employee, it won't work for you, right? So I have to go make sure that the script actually works for everybody.
Right, sure.
But totally, I know that people at H2O can hit a button and have a 16-node cluster come up in about 2 minutes. So I'm looking to get that script in a way that you guys can plug and chug. And it's not, I don't have it. And if next time I still don't have it, then I'll arrange the data set. We'll run on one node, but it'll be a fat node. And I'll tell you to get on the AWS and go get yourself a fat node. or fight the cluster fight if you want to figure that one out. And if you get the cluster fight figured out, then you can play with a lot of cores, and things will run faster. That's all I have for this go around. So, oh no, let's do this other game. How many people here feel comfortable playing around with SSH, IP port addresses, instances and servers of any sort, or AWS? Like I'm trying to take an or here. So other people look around the room. Okay, raise your hands a little higher. There's some like, I see some people like shirking here. Okay, look around. Okay, if you need help with this kind of stuff, like grab these people and ask and see if you can't get some advice. I will be a bottleneck if you're coming to me, and I definitely have people who've been asking me, and there's a limit to how many times I can answer these questions. All right, that's it. Thank you.